In this video, we will continue our discussion of molecular orbital theory. If we continue to go through the diatomic elements and go to the third element, lithium, and form a diatomic molecule, we would have some additional electrons, and now we would consider orbitals that are in the second shell. And so we need to consider now a molecular orbital diagram that not only has the molecular orbitals for the 1s overlapping to form sigma and sigma star type orbitals, but then we also have to consider the 2s orbitals overlapping. So in this particular case then, if we have 3 electrons and place them into the atomic orbitals of one of the lithium atoms and then a second lithium atom, you'll notice that we have spin pairing in the 1s orbitals, but the unpaired electrons in the 2s orbitals can then have opposite spin, and then when we go ahead and have those placed into the molecular orbitals, we then have a bonding combination and an anti-bonding combination in the sigma and sigma star orbitals of the 1s combination. That results in no net bond, and then we have to consider what happens in the 2s type orbitals. And in this case, then we fill the sigma bonding type orbitals, and that uses up all of our electrons. This produces a bond order of 1, and as a result, this is predicted to be a relatively stable species. Unfortunately, since lithium is a metal, dilithium is not something that we would expect to find as a stable species, and so we end up having more lithium metal with an extended network of atoms. If we now look at something like the dinitrogen molecule, where we not only have to consider the S overlaps, but also now P overlaps, there are the molecular orbital diagram as you see here. The 2p orbitals are higher in energy than the 2s, and you have both the direct overlap to form sigma bonding type orbitals, but then you also have the possibility of pi type orbitals. So the pi orbitals are the sideways overlapping, as you see here, and then we also have the anti-bonding combination of that. So, in this particular case, we have 2 nitrogen atoms, each having 7 valence electrons, or total 7 electrons, for a total of 14 in a dinitrogen molecule. We start to place those electrons into the lowest energetically favorable bonding, sigma bonding orbital, and then the anti-bonding orbital in the first shell. That cancels the bonding. We then go to the 2s type sigma bonding and anti-bonding orbitals. That cancels those types essentially of bonding. Now we go to the p type or molecular orbitals, and in this case we have enough electrons to fill the pi type and a sigma type orbital. And so in this particular case, we would predict that there would be a triple bond, 1 sigma bond from the p combination and 2 pi type combinations. At this point, we should consider the oxygen or O2 molecule. To the left, you see the typical valence molecular orbital diagram for the interaction of the 2s and 2p orbitals to form both sigma and pi type orbitals, molecular orbitals. You'll note that we have not only the sigma and sigma star, but also then the pi and pi star. You also have in this particular diagram the subscripts of G and U. This has to do with the symmetry associated with these orbitals in is not something that is totally necessary, but suffice to say that this is a more advanced topic. So if we take advantage of the number of electrons that we can start to put into these molecular orbitals, oxygen has 12 valence electrons. So in this case, we can start putting those into the lowest lying orbitals. We would fill both the sigma coming from the s orbitals and the sigma star. So then when we go to the next energetically available orbitals, which are the sigma from the p orbitals, we can put electrons in there. And we end up filling all the way through the pi bonding type orbitals. But at this point, we have used a total of 10 electrons, and there are 2 more left. So the last 2 electrons are going to go into the pi star type orbitals. And they go in such that they are not spin paired. In this particular case, then, if we ask ourselves what is the bond order, remember that the Lewis dot structure predicts a double bond. In this particular case, then, our formula based on the molecular orbital theory is the bond order is 1/2 of the bonding electrons minus the anti-bonding electrons. We then can count up the number of electrons that are in the bonding orbitals. So in this case it is 8. There are 4 electrons in the anti-bonding orbitals, 2 of them from the sigma star coming from the s, and 2 in the pi star coming from the p. So this gives a total of 1/2 of 8 minus 4 is 2. And so this predicts a double bond, just like the Lewis dot structure does. The thing that's a little bit unique, though, is that the molecular orbital theory predicts that this should have unpaired electrons. And those unpaired electrons should make this a paramagnetic molecule, whereas the Lewis dot structure does not indicate any kind of paramagnetic species at all. In fact, experimentally, we do know that the O2 molecule has a certain degree of paramagnetism associated with it, and therefore the MO theory is a little better at predicting what we physically measure. Just like we discussed when we were talking about the orbital diagrams for isolated atoms and their magnetic properties, when all of the electrons in an atom or molecule are spin paired, we describe this molecule as being diamagnetic. The same description would be true when we deal with the molecular orbitals as well. So here we have 2 isolated noble gases. We have helium. In the case of helium, there are 2 electrons, both occupying the 1s orbital, but they are spin paired. They're spinning in opposite directions, so this is a diamagnetic atom. Neon likewise has the same number of plus 1/2 spinning electrons and minus 1/2 spinning electrons, so this would also be a diamagnetic atom. If we consider a situation where there are more electrons that are spin 1/2 than there are minus 1/2 spinning electrons, then we end up with a paramagnetic species. And so this is the orbital diagram for an oxygen atom, and as a result, the oxygen atom, an isolated oxygen atom, would be considered paramagnetic and would be attracted to a magnetic field.